Okay, welcome to Chapter 4. Chapter 4 is on site surveys. I brought you up to the roof of my apartment building so you can see exactly how to do this. This is the roof of my apartment building. It's a flat roof. The first step in a site survey is to actually go to the physical location and assess the quality of the roof you're going to work on. This roof is brand new. It's absolutely beautiful. It's well maintained. You can see it's a flat style roof with a small slope. The direction you're facing right now is south. It's evening time. The first step is to go up, assess the roof, see how much area there is. We're going to take some quick measurements and we're going to note all of the equipment. We're going to note the satellite dishes, we're going to note this, and we're going to note the locations of the trees. Generally at this point, we would use a solar pathfinder to find the area of all the shading. I'm going to post a link to a video on solar pathfinding. I'm going to show you how to use the trigonometry to do all of your calculations on your shading. So just post up. The next step after you've made a site layout drawing is you're going to want to measure. You're going to want to take your compasses. Right here. And you're going to want to find the places where there's going to be shading. Now, right here at this site, you can see up to the south we have some really tall pine trees. What we're going to do is we're going to measure the angle of those from vertical, and we're going to find the angle they are from true south. The way you find the angle they are from true south is you take your compass, you set the magnetic declination, which in Southern California is 12 degrees. You line that up with your site drawing. You take your sighting compass, you line it up to due south. Anytime you're ready, buddy. And you sight the tree.
Peter, I can't see it.
Well, you gotta sight the tree. That tree's at 150 degrees. That tree's almost exactly south, 180 degrees. This tree. $200 degrees. 215 degrees. You write those down? Then we're going to take a protractor and we're going to determine the angle that sits above the horizontal axis. Above the horizontal axis. From that we're going to figure out approximately how wide it is, about 5 degrees wide, determine how high it is. From that we're going to be able to determine the year-round shading using our sun charts. Go back inside, I'll show you how to do all of that. Okay, welcome back into my house. After you go up and you actually see the site, let's talk a little bit about site surveys. The first thing we're going to do is we're going to check the slope of the roof. That was easy on our roof. It's a flat roof, it has a slope no more than 5 or 10 degrees. Check the quality of the roof. When you check the quality of the roof, you want to check for Roof deterioration, you want to check for age, you want to check for obvious slumping in the roof. If there is any kind of significant deterioration, you're going to want to call a structural engineer and make sure that that roof can carry the load that your array is going to put on it. You're going to want to check for obstructions. In ours, we had satellite dishes, we had two big tops of stairways, we had AC units, roof vents, all of which have to be noted in the design drawing. You want to find the available roof area. Finding the available roof area is finding the portion of that roof that remains unshaded from 9 a.m. to 3 p.m. all year round. And to do that, you're going to have to check for shading. You're going to want to find an area and check for shading. The most effective and best way to do this is to use a solar pathfinder or a digital solar eye. There's another way to do this that involves math. I'm actually going to post on my video a very good video I found on someone teaching people how to use the solar pathfinder. I don't own one, so I'm not going to put that video up myself. If you were to do it the long way, there's two things you really have to understand. You have to understand this solar chart that we went over last time, and you have to understand solving a shadow distance for a known height. All right. The first obstruction we had out there were trees. Now, if you take a look at the site survey, this is our site drawing. This is the area we wanted to put our solar array in, and there were three trees. One at 180 degrees, one at 200 degrees, one at 215 degrees. They're both about 5 degrees wide, and the angles that we measured with a protractor by taking a level plane and angling up from the ground. The 180 degree tree was at 26 degrees, 200 degree tree 31 degrees, and the 215 degree azimuth angle tree was 15 degrees above level. Okay. And the other real obstruction we had was it's the top of a stairway. And with the top of the stairway, I was just able to measure its height. So we're going to solve these two problems differently. First, we're going to do the trees. We'll go back over here. Okay. I just want to thank my girlfriend for being camera person on this one. Very, very cool of her. I'm stoked. Okay. The way we're going to find a shadow distance for a known height is we're going to use this formula. This formula is the theta equals the arctangent of the height divided by the distance. The angle we're actually going to solve for is the angle that the sun is always between 9 a.m. and 3 p.m. This is the solar chart for our area. Now, 9 a.m. is right here, 3 p.m. is right here. That is the angle we want to solve for. Okay? That angle is 25 degrees. Objects that have an altitude angle of less than 25 degrees will not affect shading between noon and between 9 a.m. and 3 p.m. solar time in this location. That angle will vary depending on your location and your latitude. Okay, so the first thing we're going to solve is that the top of that stairway. We happen to know its height. Its height is 11 feet. Okay? Distance. That's going to be the length of the shadow. So the arctangent of that 11 over the distance is equal to the theta of the angle, the theta, which is 25 degrees. Okay. So in order to do that, just a real simple calculation, you take the 11 feet, or the distance, we'll take the distance over this side, and we'll take the 25 off this side, and it ends up with the arctangent of 11/25 is equal to the distance. And the distance, and I just happen to have already done that, it's 23.75 feet. It's 25 feet. I mean, it's 24 feet. And what that means is the top of that stairway that's 11 feet tall, when the angle of the sun is 25 degrees, is going to cast a shadow that's 24 feet long. Now, in our design drawing, what we have to do is we have to take this distance and pull it back 25 feet, and that'll be the unshaded area. Okay, so now we're going to deal with these trees. To do that, we're going to go back right over to our sun chart, and I'm going to find a Sharpie dry erase marker that works. All right, so we know that this first tree was at 180 degrees. It was due south, so we marked that on our sun chart. And we know that the angle of this tree, by measuring with a protractor, was 26 degrees. And it's about 5 degrees left to right. So it's going to shade all of this area in here. As you can see, the sun path, it will never cause shading on the area we measured from. Okay, the next tree at 200 degrees is at a height of 31. It's going to cause shading all through that area. 220 was at 22 degrees. It's going to cause shading all through that area. Now, because this is 9 a.m. to 3 p.m. solar time here, the only tree that's going to cause any amount of shading is going to cause shading right here in this area. It's going to cause shading in the month of December, January, February, and it's going to cause shading from approximately 2 p.m. solar time to 3 p.m. solar time. And then as it drops down, it'll also cause shading, from 3 p.m. to 5 p.m. But because what we call like the solar window, the peak sun hours of any location are between 9 a.m. and 3 p.m. solar time, that isn't going to affect the production of the system in a significant way, in a way that will affect our calculations. This portion right here will cause a significant drop in those months because it cuts almost an hour and a half off of our peak off of our peak sun hours for those months: January, February, March, October, January, February. Yeah. The rest of the months, June, July, August, those are going to be completely unaffected by that tree. In those 3 months, we're going to lose an hour of time, and we're actually going to lose about 10% production in those months. Again, the best way to do this is to use the Solar Pathfinder or the Solar Eye. If you have to do it this way, it's good to know that this exists. This particular method is good for a single pole. If a single light pole is in your way, just figure it out like this. This determining the shadow at a known height is good for obstructions that are easily measurable, something that's going to be easily in the way all the time, and to determine how far back from that object you have to put your solar array. Okay, so now that we've determined the shading on the area, and we've done our site analysis, we've looked at the roof, we've determined that this area on our map, we've moved back from this, the designated amount, and now we have this area. This is a suitable area for an array, in red there. Okay, and that measures about 25 feet by about 19 feet across. That's a lot. It's time to talk about this formula. This is a formula that exists and is on the NABCEP exam, so you should know it. this is the required area for the array formula. It says the area required is the peak power production divided by 1 kilowatt per meter squared multiplied by what's the name of that thing? ETA. And ETA is the symbol for efficiency. This is you can use this formula, but this formula will not give you an accurate number because of things like inter-row shading and spacing, especially if you have multiple rows of modules. If you were to put the modules right next to each other and lay them down, this would be a formula that would give you an accurate answer. But because in our particular situation we'd have to put multiple rows of modules that are tilted at an angle, the modules will not be directly next to each other, so our area will be significantly decreased. Okay, another formula that you're going to have to know is the formula for slope. Slope is rise over run. Use this for determining the angle of a roof. In all practicality, just use an angle finder. It's the way things are done. Okay. The next thing we're going to talk about, I talked a little bit on the roof about solar declination. Solar declination refers to the difference between the Earth's magnetic field and true south. The Earth's magnetic field, except if you're about on the Mississippi River Basin, is different than the actual true south. And this is because the lines of force actually move outwards as it gets closer, and they move in significantly different ways. In Los Angeles, our declination is 12 degrees. And the way you do that is it's a positive declination, so you add it to your degrees. If we're at true south, we'll add 12 degrees. If we're at magnetic south, that our compass shows, compasses always show magnetic south, and we move 12 degrees over, that will give us true south. Okay. The next thing we're going to have to talk about, the two things needed to really determine the size of an array, the size you're capable of having and the size you need, is the load requirement. Every house has a load requirement. Everything you have in your house that's electric draws a load. And you need to determine what that load is. The best and easiest way to do this is you take your power bill. For the last couple of years, you divide it, you add it up, and month by month you get your average daily load, just, simple averaging. The other way to do this is you create a daily use chart. And the formula for this is your load in watts multiplied by the quantity of those loads, multiplied by the hours of the day that you use that, multiplied by the days of the week that you use that, divided by 7, which is the days of the week, and then that'll get you watt hours per day. For example, my television, on the back, and there's a picture of the labels that every appliance is required to have. It'll show you its voltage and amperage and its wattage draw. Some appliances only put the amperage on there, and it's very easy to determine. As you recall, volts times amps equals watts. For example, my dishwasher just says it's 8.6 amps. Well, my power is 120 volts times 8.6 amps equals 1,032 watts. Okay, my TV. My TV is 155 watts. I have one of them. I watch it for 4 hours a day. I watch it 7 days a week. That's a lot of TV. It's important to be realistic on these if you want even close to an accurate number. That equals 620 watt hours per day. As you can see, I've listed all of the appliances in my house. The fluorescent light in my kitchen. I have a Macintosh. There's 3 laptops in the house. There's an aquarium light that draws almost 1,200 kilowatt hours a day. Dishwasher, vacuum, and then a list of small appliances. Which brings my kilowatt hours a day to 26,574 watt hours per day, which is 26.6 kilowatt hours. Okay. This is going to be the number you use to determine the number of modules that you need to achieve your daily load. And you'll use this number differently in different types of systems. In a battery-based independent system, you're going to use this number differently than you will in an inverter-based system. But it's important to understand your average daily load, and this is how you get that. That's that formula. Cool. Film me, I'm doing stuff. Okay. On this side drawing, I just want to talk about a few other things, a few of the restrictions. We determine the shading, we determine the area. There's an area right next to the edge of the roof called an easement. Depending on your local code, you may need an easement all the way around your array. You may need an easement just on the side closest to the edge of the roof. But check your local code and make sure that your easement is included when you determine how much area you have for your solar array. The next thing we're going to talk about is how to put when you put a module on the roof, especially a flat roof, it's not going to be laying flat on the roof most of the time. It's going to be tilted up at an angle. And because that panel is tilted up at an angle, it will cast a shadow. And determining the length of the shadow is similar to determining the length of the shadows that we did earlier for the standing object. The most ideal angle to mount modules is equal to that of your latitude on the Earth. Los Angeles is a latitude 34 degrees north. Our modules are going to be mounted at 32 degrees. And that means you can determine their height very easily by using a tangent. I know that the length of my module, because I looked it up, I just looked up the dimensions of my Sharp module, it's 65 inches long. And if I put a 65-inch module at a 35 degrees, I know because, I can get the tangent of 34 degrees is equal to the height over 65. So that equals 43 inches. The height of this module is going to be 43 inches off the ground. That's helpful not only in determining how much shading, but if you have a huge number of modules to go up, these standoffs can actually be pre-cut and drilled before you even drag them onto the roof, saving you a lot of time, saving you working on the roof, and saving you clutter on top of the roof. Okay, the distance between rows of modules is called, the inter-row distance. And there's a formula for it that takes into account not only it takes into account the angle of the sun, it also takes into account the azimuth angle, which is the difference between the direction that your array faces and the direction of south. So because our array is not facing directly south, it's actually at about 190 degrees, 10 degrees off solar south, that'll come into play with this equation. Your equation is actually the distance between the modules must be the height of the module, and that's the height we just figured, multiplied by the cosine of lambda, which is, this is equal to the azimuth angle subtracted from the azimuth angle of your array. In our case, 180 directly south, subtract 190, which is the angle that our array will actually be mounted. If you have a sloped roof, this angle will be the same as the azimuth angle of your roof. Okay, over the tangent of the solar altitude. And you want to use the minimum solar altitude. That's the same solar altitude we use to determine on our charts. It's 25 degrees. Okay, so the distance between modules has to equal 43 inches multiplied by the tangent of this, which is 10 degrees, which is 0.98, over the tangent of 25 degrees, which is 0.46, and then equals 91 inches. That is actually the distance you will have from the back of this module to the front of the next module. There's a rule of thumb, it's 3 times the distance, and that's a good rule to use if you're doing larger size commercial projects where space is really close, or you want to get really close, put as many modules as you can and measure an exact distance. This is going to give you that exact distance that will give you 0 inter-row shading. Thanks so much. This is the end of it. This is the end of chapter 4. On the next video, we're going to go over battery bank sizing and factors that go into that. Thank you very much, and we'll do it again.